As I was saying, thank you for joining us, the panelists and also the attendees. Today is the second webinar of the week. We were so popular this week that we had to split the webinars in 2 days, one yesterday and one today. We will have a great presentations from yourselves, the panelists of this new innovative technologies that are coming up on, I suppose, on plasma, I suppose plasma thrusters or whatever they are. But let's. I'm going to leave everything to you to show and to present. So I'm going to start with my presentation now. So I will ask the panelists to stop their video. I'm going to speak for about 5 to 10 minutes on ACCESS.SPACE Alliance in the webinars, and then I'm going to call on Matthias first, then Dejan, and then at the end we'll have Marcus to present on that order. Okay. So our webinar will be recorded so that we can watch it after this live webinar in the future for people to look at it. Okay, let me provide you with a brief, and please let me know if you don't hear me well, or if you the video is not seen properly. Just speak up, the panelists. I have no other person that can tell me what I'm doing. We are here with ACCESS.SPACE Alliance to help the sector to overcome this COVID-19 issues, because a lot of people and companies are having their staff being working from home, for example, even though we are now coming into release, into a period of release and actually starting to work from workplaces. So it's to support also companies on their PR side to start growing as well for these new SMEs that are coming up. So to do some PR for them. We're going to proceed today. Each of the panelists will have about 15 to 20 minutes presentation with 1 or 2 questions at the end. So in total, we're going to have about an hour of presentations and Q&A. And then we'll have a 15 minutes wrap-up session with questions as well. From the audience and myself, so a little bit of a discussion with the panelists, and of course to make the webinar uninterrupted, we're going to have everybody muted. I may or may not ask at the end people to ask their question, depending on our time and depending on the questions. Okay, I would like to thank NeutronStar Systems to sponsor our webinar today. Thank you very much, Marcus and Manuel, for sponsoring our webinar today. This is only for cost recovery of our platforms. The panelists today will be Manuel and Marcus from NeutronStar Systems, and then we'll have Matthias from Krisol, and then Dejan as well from SPARC. 3 different companies in this innovative technology. So here we have all the webinars that have happened in the past 13 weeks, in effect.
Sorry, Tony. Sorry, the slides aren't showing.
All right, Matthias, can you see my slide, any chance?
Yes.
Matthias,
I see your face, but I can't. At the moment, I only see your face.
All right. Okay, let me just. Thank you for letting me know.
Mm-hmm.
Maybe something happened with my transmissions. Just a second. All right. Share screen. Let's do it again. Okay. No. Let me go back to stop share screen, and nope. Apologies for this. Let me just see my. Okay. Let me see if I can start over again. Stop share. Share screen.
You had it there for a minute.
Yes, saw it as well.
How's that?
Oh, no.
Works.
All right, so I'll start over again. Can you see it again? I'm now in presentation mode.
Yes.
All right, perfect. Thank you so much for letting me know. So I'm not going to go over what I just said. So Intro, the sponsorship from this webinar. Thank you, NeutronStar. Thank you very much for sponsoring our costs. Then the panelists on the slide, you can see that we have Manuel and Marcus from NeutronStar. And also that we have Matthias from Krisol and Dejan from SPARC. The Space Alliance webinars in the past 13 weeks are listed here. This week's webinar is today's webinar, in effect, because we have one yesterday. It's key technologies for high power missions. We're going to have also a webinar next week on orbit servicing, propulsion, and situational awareness. And I'm preparing also a panel for week 15 around the 16th of July. I'll be in Italy, in fact. I think I will be able to do that. We're going to have an IITU panel. I hope everybody will join us. This webinars, we have 145 individuals who are registered. If I go live, we have 59 who actually attendees at the moment, from 34 different countries. These are the past registrations that have happened in the past. You always see that about 60%, 50–60% of the registered people attend the actual webinar itself. I'm not sure why people register and then they don't attend. Maybe connectivity or whatever. Maybe the time difference between Asia or Pacific time is a bit too much for them. Type of attendees to the webinar today that are registered are listed on this chart. I'll send you the charts later today or tomorrow. You can read it yourself. There's a wide variety of people who are registered and attending these webinars of different disciplines. And also, thanks to Alice, she's put all the videos of the recording of the webinars of the past 12 weeks in YouTube channel. Once I send you the slide, you can access the past webinars through this link I'm going to send you. Let me just talk briefly about ACCESS.SPACE Alliance. Myself, Betty, and Christian have founded the ACCESS.SPACE Alliance thanks to the idea that Betty had about 2 years ago. We founded the company here in the UK on March 2019. It's a non-for-profit company, limited by guarantee. And recently, Alice joined us to help us into managing the data and the recordings that we are doing. Then the ACCESS.SPACE Alliance is here to unite and represent the small satellite sector, but not only the small satellite sector, but the SMEs that are interested in this field. Not necessarily from one single country, but from a global perspective, helping to connect, advise, advocate, promoting and research, and also producing standardization for the sector where is needed, basically. We have 83 organizations who have so far joined us. They're listed here on the slide. And also we have 2 partners organizations so far from India, from China, that we can collaborate if needed in the future, as well as we have an MOU with the European Regulatory Office in Denmark, where we can actually represent the interest of the sector from a perspective of licensing and frequency management and frequency spectrum management for their benefits, basically. So we can attend those meetings as an observer, and soon we will be also a member of the ITU and also UN Corpus in Austria, which is the body that deals with space law and space objects, basically registration and so forth. Our members are pretty much split between 1/3 in the UK, 1/3 in Europe, and about 1/3 in the rest of the world. Majority of the rest of the world is basically USA, but 20% of the companies come from the United States. And last but not least, we're also here to help companies to find professionals in need of a job or an internship, for example, new graduates, placement. If you are interested and you have placements and opportunities, please contact myself and we can provide you with potential leads. I have a bunch of CVs available to share with you if you need. Okay, now we're ready to start the webinar. So I think Matthias will go first. And then once Matthias and the questions are answered, we'll go to Dejan, and then at the end, we'll have Marcus presenting as well. So Matthias, the floor is yours. I'm going to unshare the screen. Oh yes, I will have to present the presentation myself for you. Let me just go and find it first.
I just unmuted my mic. Can you hear me now?
Yes.
All right, good.
Okay, in 1 second, I'm going to
Yep.
just go back to the, I have a presentation open. I'm going to stop my screen, and then I'm going to share my screen with your presentation. Just a second. Let me know if you see it, and then I can mute.
I can see the slides, but not yet in presentation mode, but I can see it. Yeah, now it's good. Yes, perfect. So can everyone else see the slides as well in presentation? Yep. All right, so it's time to start. Huh? Okay, just a second. All right. First of all, thanks a lot to Tony and also to my friends Manuel and from NeutronStar, because they actually invited me to join this webinar. I did not actively seek this opportunity. I am modest enough to say this is really for me an invited webinar pitch. And I thank both of you to invite me to present this to a larger audience. To start, I'd like to, it sounds a bit not so modest anymore, but this is actually like a baby version of a much more ambitious project. This project is the result of many years of lobbying for a gigawatt scale photovoltaic project, which would have been $1 billion business. And unfortunately, it failed in the lobbying for funding. It was, I would say, political friction. But what was left over is still the same core technology. Has a long history, but I will present just the key ingredients for you today. Can you move, please, to the first slide? I start with a historic slide as a motivational introduction. And for those of you who don't know how old I am, I'm actually a fan of Queen. That's my generation. So when I was a teenager, Freddie Mercury was my biggest idol. And there's a famous song from him that's called "Don't Stop Me Now." With one of the song lines is, "I'm a shooting star racing through the sky, defying the laws of gravity." And this is actually the intro for this presentation. This is a historic image of reckless entrepreneurs, I would call them, the first alpinists who climbed successfully the Eiger North face in the Swiss mountains. This is an incredibly dangerous climb. Look at their equipment. I think nobody would dare nowadays to work with this equipment. It's also fairly heavy and a bit cumbersome to work. Can you please move to the next slide and I'll show you the difference to today? Yeah, this is the Eiger North face, and to climb up there, it's actually quite dangerous. In 1938, it took 3 days to do the pioneering climb. And at the bottom right, you see the current world record holder is a Swiss who unfortunately died in the Himalayas with a training session. He died in 2017. That's Uli Steck. He climbed the same north face in the same route in 2 hours and 22 minutes. Can you imagine that? From 3 days to 2 hours and 22 minutes. And that is, of course, due to modern equipment. But one of the key differences is ultralight equipment. Look at his equipment that he has. He has only ultralight red carbon, picks, ice picks, very light helmet, very light clothing, 300 milliliters of water, and the Hershey bar, and that's it. Nothing else. He essentially almost ran up this mountain. And there's no other way to do that than by using the most extreme low weight technology. And that's actually the motivational introduction that I did for my technology search. Which is the motivation. If you go to space, if you want to defy the laws of gravity, you have to reduce the weight of your equipment by all means. Please move to the next slide. When we took a historic picture at photovoltaic power generation in space application, I would call the old space niche, starting in the 60s with satellites, the standard technology was always crystalline silicon. Nowadays, I think it's crystalline gallium arsenide technology, and these crystals had the risk of being damaged by space debris. For example, microparticles from meteorites. They can be very small, but they have very high speed. And if they hit the solar cell, it looks like in this typical image on the left. You actually punch holes, you break the cells, and you quite often also create short circuits. That was one of the reasons you wanted to optimize watts per square meter. In other words, have a high aerial efficiency of the PV array. And that restricted, of course, also the choice of materials. Now, in the new space, as we start to talk about now, the design figure of merit that we should actually think about is not only watt per square meter, but also watt per kilogram. In other words, if you want to have a long space mission, you have payload issues. You want to get lots of possible payload up to, for example, the Moon or to Mars. And then the total payload is a critical parameter. And any additional equipment or required for example, components for power generation should not be too heavy. So if you optimize for watts per kilogram, you can start to use different technology. And that's the core of my technology joint venture. Please go to the next slide. Okay, on this image here, which is courtesy of my joint venture partner, Krieger from Huntsville, Alabama, that's an established supplier of NASA, is actually the only company in the world that is able to manufacture polyamides in this very thin polymer foil, optically transparent polymer foil, which is now rated for space harsh, radiation harsh. In other words, there are applications in space which are guaranteed for almost 20 years of radiation exposure. Although this polyamide is a very thin foil. Here in this case, it's a solar sail, which is coated by aluminum. In other words, the foil is transparent and is coated by aluminum to form a reflecting sail. This is deployed here in a carbon deployment structure. The total weight of the deployment structure, including this 400 square meter area solar sail, is 32 kilograms only. Now, and this is the core of my technology that I propose here, when you use thin film PV technology that we designed at PV Center in CSM, directly on this foil, you can actually reach, instead of 200 watts per kilogram, which is called for by a recent ESA call on the table below, you can reach 1,370 watts per kilogram with the same structure, which is already space flown. The second advantage is you have an enormous advantage in high stowing density, because if you don't have a crystalline structure, the area is not such an issue. You can actually easily deploy it to a very large area. In other words, you can store 60 kilowatts per meter cube. No, sorry, not 60 kilowatts per meter cube is an ESA requirement for a recent ESA tender, and we can achieve 250 kilowatts per meter cube with this. So almost an order of magnitude better than what ESA required. Move to the next slide, please. Where is this advantage biggest? So in other words, if you work with a thin film PV array, which is deployed at a very large area, the disadvantage you have is you need a larger area for the same power, because amorphous silicon has an aerial efficiency of around 12% in space, and gallium arsenide about 28 to 30%. So of course you need a higher area, but the weight advantage is dramatic. And this is rather proportional to the weight of the total power, for example, propulsion system. In other words, the bigger, the better. I know this is not good for small space applications such as sat cubes, but if you go to, for example, Mars missions, as you see in this table here, the advantage of using this technology for powering, for example, ion electric propulsion are absolutely dramatic. I used some reference papers from NASA, I'll show you later, where we estimate just the payload benefits which we can save and use for a cargo instead of fuel of up to $70 million for one Mars mission alone. So you would actually pay back the R&D almost in one mission. Please move to the next slide. This is an overview table of different technologies that we currently compare with. So the standard technology for space, crystalline silicon, gallium arsenide triple junction, is quite mature. You see that they're also used for space, but they're just heavier, and there's not much room for improvement because they're more or less close to the physical limits of deployment. The one in the pink column are the polyamides from my technology partner Krieger in the US. And this is either lanthan RCCP1 or Corin. These are two different materials. One is optimized for LEO orbit, so this is for lower Earth orbit satellites, and GEO and deep space missions would be for example, Corin. This is the best material available on the market. We can design photovoltaic power arrays with up to 1,370 watts per kilogram specific power. Please move to the next slide. Yes, there's actually a table, just a table where I calculated the estimated benefits, watts per kilogram for standard technology, gallium arsenide, and compare this with the technology that I propose. And you see that the payload cost alone are so high that even with a LEO smaller 50 kilowatt power array, which is not a very big one yet, you can save with one mission $2.5 million, and with a GEO orbit space mission up to 10 million, just with 150 kilowatt array. So the bigger the power that you need, the bigger the saving. It's almost directly proportional to the volume. Please move to the next slide. There's one more. Okay, this is a reference paper that I studied actually to calculate this advantage. It's a paper by NASA where they calculate the Mars mission, and this contains several stages of transportation. The first one, chemical fuel, and this absorbs most of the mass of the rocket. And the second stage, of course, is the electrical propulsion, where we will hear more about later. It makes only sense to use this for ambitious missions where you actually need a deep space electrical propulsion with photovoltaic power generation. If you combine the lowest weight technology there, and if the mission is big enough in size, the advantages actually, they almost explode. With one of the reference missions here, we estimate $70 million savings in one mission only. Please move to the next slide. So what is actually the core of my joint venture? My company is actually a legal technology joint venture between two established companies. First is my current employer, CCM in Switzerland. That is an established public-private partnership with research technology teams. And one is the PV Centers, the largest photovoltaic research center of Switzerland, headed by Professor Balif. And this would form a technology joint venture with Nexol USA in Huntsville, Alabama. And this company is the only NASA rated supplier of thin film polyamides, which are space rated. They are willing to work exclusively with me in this joint venture, and this combination would allow us to actually disrupt the PV array design for space applications. It doesn't make a lot of sense to go for very small arrays because there the relative advantages becomes almost negligible. So that's why I think the focus on high power mission makes a lot of sense. Please move to the next slide. This is from the outside, the PV center in Neuchâtel in Switzerland. That's just a snapshot of the clean room and process equipment that we have. These are R&D tools. And in the middle, you see actually the R&D samples that we designed several years ago already with the predecessor company of Nexol. At that time, they were part of Mantech Corporation in Huntsville. And these are solar cells directly coated on this polymer. These are the brown dots, but this is just 0.3 micron thickness. The total cell thickness with the substrate is about 6 to 7 microns. And specific power for this cell without an array is almost 4,000 watts per kilogram. So this is really a world record in terms of specific weight. Next slide, please. Okay, we could actually use this technology for different space applications, but clearly the two most important ones where we can start talking about business cases are the two on the top. Communication satellites are a more established technology, but with these PV arrays, we could actually empower them with a lot of power and actually reduce the weight for the total satellite and pack, for example, scientific instruments to save weight for the PV arrays. This is a potentially attractive application. But of course, the technology readiness must be a bit better. Then I think what we discussed today, the most important one is the electric propulsion for Mars and deep space missions. If we combine this with the technology from NeutronStars, we can really disrupt this technology by more than an order of magnitude of benefits for all parameters for the mission. So that's where I see the biggest advantage. Next slide, please. This is the roadmap where we plan to go next. And of course, it's not a cheap thing to do because what we have here is a high-level TRL for the basic components. The polyamides are actually NASA rated and flown in space at TRL 9 and 10. The amorphous silicon PV technology has been flown in space on steel substrates, but it has never been combined on this polymer in a form of a serially interconnected power array, which is of course required to get high voltage in an array. You need to serially interconnect hundreds of cells into one power array. And that's what we need the funding for this business case. We need to design and upscale the production for large area, but the basic technology, both from the solar cell side and from the substrate, are very mature and flown in space. So the TRL is only low on the level of system integration. That's what I want to say with this roadmap slide. Next slide, please. This is just an overview on the funding requirements. So it's certainly not a cheap technology project, but I just showed you before that if we use this technology for a Mars mission, within one mission, you gain $70 million for payload benefits, which otherwise are not accessible for payload. And if you do that in a total budget calculation, you would actually have a positive return on investment in one mission. That's what I want to say with this slide. Next slide, please. I think it's almost finished. Yeah, this is the summary of the two coordinates. My role is the CEO of this joint venture. That was my ambition for the last years, but I'm currently associated with CSCM. I'm doing business development on behalf of CSCM. I would, with this joint venture, then charge these two companies, CSCM and Nexolve, with the technology development, and later for Krisol would commercialize the products and sell them to space mission providers. I think that's the last slide. One more, I think it's a summary slide. Yeah. Or is one more? No, I think it's the last one. Yeah.
That's the last one.
I think that's it. Thanks a lot for your attention. I think I just hit the time limit of 40 minutes and 58 seconds.
All right.
Thanks a lot for your attention.
I would like the audience to ask questions. So I'm going to, there's one already here from Vipin from India.
Okay.
What are the barriers for mass scale application for transportation, etc.?
Barriers for what? Sorry, I didn't understand the last part.
Barriers for mass scale applications.
Scale.
Mass scale application. You can read the question actually on the box below.
Let me check in the chat window.
Yeah.
Barriers for mass scale application transportation. Okay. I would say in terms of manufacturing, I don't see a lot of limitations. And the process equipment, for example, that we use is used for the display industry. So it's the same technology that we use for LCD television displays. It's the same PECVD technology. And some of the reactors in the market are actually large areas. So if we get access to these equipments and transfer the process to these machines, there's almost no limit. So we could actually easily manufacture megawatts or gigawatts if you have enough equipment. That in principle is almost no limitation. I don't know what the question means in terms of barrier to mass scale. What is mass scale? For the space industry, as far as I know, in PV is about 1 megawatt total PV power per year, which is on the market. That's the current world market for space, is around 1 megawatt. From the technology that I propose here, this is absolutely there is no limit to that. It could easily go orders of magnitude beyond. If you find customers willing to purchase, I see no limitation at this stage. Okay.
Richard Sharp, could you ask a question live to Matthias?
Okay. I see that I can read it. Yes.
Richard, are you there?
Okay.
Okay. Yes, I can summarize.
Can you reframe your question in orderly? I'll listen.
Yeah, just for the benefit of everybody listening. Sounds an exciting development you have there.
Where are you from? Can you tell us where you're from, Richard? Which company?
Yeah, my affiliation, I'm with Cobham Rad Europe, based at Harwell. We provide environmental testing services for the space environment, particularly radiation and thermal testing.
Okay. Well, this is actually verified by my partner Nexolve, and as I said, Nexolve is an established NASA provider, and this material has been flown in several space missions as a solar sail, as I showed you in the image, with aluminum. So material is coated by aluminum, and is used as a reflecting sail just for solar sail. A solar sail is a concept where you actually propel a low weight satellite object with just solar, how do you call it? Photon transfer, so photon impact transfer. This is the way solar sails work. It's a very low acceleration, and for that you need to have a very low weight construction. But this has been flown in space, and the material is NASA rated for 10 to 20 years performance in harsh environment, which is fantastic. I mean, they have about 20 years of heritage of technology development, and this technology has never been used in combination with our PV thin film, which I find a bit a shame, because when you look at the combination, it's absolutely astonishing. So the combination has never been tested in space, but the polymers themselves, they are NASA rated and specified for space. So they are guaranteed by NASA and approved by NASA. What has never been done is we have never coated a serially interconnected PV array on these materials. This has never been done. It needs to be developed, yeah.
So Matthias, just a very quick answer to the last question, then we need to move on.
Yes, sure.
From Ramesh, can you read the question out? And then
you mentioned the TRL is only a recent system.
Could you read it out, please? Maybe because people don't.
Okay, you mentioned the TRL is 1 year based on, no, this is maybe a misunderstanding. The TRL is the NASA level of readiness for applications. I would say the TRL for the material is 9 to 10, so it's flown in space. The TRL of amorphous silicon thin film PV cells is also 9 or 10. It has been flown in space on steel, as far as I know, not by us, but by other companies. The combination has been tested on breadboard only and on single cells. So we have tested actually single photovoltaic cells, 0.8 volt open circuit voltage in the lab, but that's TRL 3. So this is a low TRL, but you base actually the combination on 2 high TRL subcomponents. It's a bit hard to understand why this total system is still low TRL, but the risk, in my view, is fairly limited. Because if you work with such reliable materials, the combination should be a challenge, but feasible. No.
Okay, we're going to move on to Dejan. Please do not answer the questions on the Q&A box. I will ask them afterwards. So don't touch anything. So Dejan, can you come on board?
Yes, 1 second, please.
Sure. And also, Matthias,
You hear me?
remove your video. Yes, so I can see you. I can see your presentation. You're on now, and perfect. I'm gonna.
Okay, and I guess we can start.
Yes.
Okay. So, hello everyone from my side. My name is Dejan Petkov. I'm the CEO of SPARC Industries, company quite young, 2.5 years old, founded in Luxembourg. Before I start, thanks Tony for giving us the opportunity to present here on this platform. Also, would like to, just like Matthias, to thank NeutronStar Systems, because they have invited also us. So that's how we found this opportunity, so to say. So today I would like to present our technology, what we're working on. Today's talk structure is as follows. I would like to give a snapshot on how we perceive the situation in the electric propulsion development and plasma simulation community as it is today, how we would like to improve the situation with our technology. We'll introduce some high-level features and, of course, explain what added value we provide. We'll go slightly into detail regarding our software, and also would like to present our vision regarding how EP plasma simulations will be performed in summer 2022, which is the moment where we will release our product. And of course, I would like to finalize with introducing the partners we're currently working with. So, you see the video is working? No feedback, yeah. I take. Oh, okay, it's okay. So without going into details, into history, just 4 observations that we can make today regarding electric propulsion development and how this relates to plasma simulations. So one observation is that today the plasma simulations tools that are available that are targeted to electric propulsion systems have been primarily made by scientists for scientists. So this is one major observation. The other observation is that if we take the area of the plasma flow simulations as one work part and the thruster engineering and design work as another part, these 2 parts are very loosely coupled. And this relates to the 3rd point, where we can observe that the plasma simulation experts and the electric propulsion engineers do not really talk to each other. And the 4th point is a little bit like a let's say consequence that in the whole thruster development process nowadays, the plasma simulations play a very, very minor role. So these are the 4 major observations I'd like to present here. And the reason why I put this video there is because some years ago, before we founded SPARC Industries, we have been developing an electric propulsion prototype. The company Gradel in Luxembourg. This prototype has been tested 2017 at the ASTEC facilities. And 2 things are worth being mentioned here. First, we have been targeting to extract a certain jet beam for propulsion purposes based on a specified and characterized jet mode of operation. And we figured out that this jet mode is actually not that beneficial for space propulsion purposes. And the second thing is that worth being mentioned is that the jet mode that you see here, which is stable and seem to have benefits for space propulsion purposes, is actually something that we didn't expect. And we didn't expect it because that jet mode has never been described in literature. And it was a moment that describes very well that we would have, being able to use a simulation tool that allows us upfront to exclude design configuration, and even more to maybe optimize valid design configurations would be very, very helpful. In fact, we've been looking back then for simulation tools available in Europe, in the US, worldwide, and we're really happy. And so back then we started to write our own code. So first-hand experience from an EP development perspective. So we continued developing the software, and which brought us actually to what we're doing predominantly today in SPARC Industries. We're focusing on 4 major features. Let me just quickly move this bar away such that, perfect. On 5 cornerstones in order to provide the added value that we promise to the customers. So first thing is that we deploy state-of-the-art software within a targeted application spectrum. So the software that we develop will not be applicable to one application, electric propulsion technology, but also not be that general that can be applied to any electric propulsion technology out there. So it's going to be a spectrum that will grow over time. Performance-wise, of course, in order to bring added value, it has to perform or to deliver credible results on industrially relevant timeframes. Regarding reliability or software quality, this is something that we achieve by applying modern software paradigms and industrial software quality standards, something that's also not common in the plasma simulation community, which is primarily science and academia driven. The 4th point is ease of use. When we want to bring added value to the users, and then we have to put ourselves in the shoes of an electric propulsion engineer. What's his perspective on this, on integrating and using such a tool in a daily work? And the 5th point is the applicability. So we don't develop something, but what the thruster developers are telling us they need. So if we move on, it brings us to the value proposition. So there are 3 points that I would like to outline here. The first one is the most obvious one. Nowadays, the major part of the development cost comes from design variations and experimental campaigns in order to see whether this design fulfills the requirements or not. And at the very end of the design, there's the qualification campaign, which takes very long, but is required in order to prove that the lifetime that is required for the mission is really provided by your propulsion system. So there's a lot of potential for reducing development time and cost if you can make a certain set of experiments obsolete. And the second added value that we offer is the increase of the competitivity. This comes simply from data that our tool will be able to extract from the simulations that is highly interesting for the satellite manufacturers, so the customers of our customers, and they currently do not get by the EP suppliers, simply because they either cannot get this data by experiments, or they can get it by experiments, but it's way too costly and would make the EP systems price explode. So providing additional data about the electric propulsion system that the satellite manufacturer can use for the integration of the thruster into the satellite increases the competitivity. And the third added value is that with such a software, properly designed and implemented, we'll be able to reduce uncertainty-driven design margins. So these design margins are, as I said, uncertainty-driven, coming from not knowing the landscape of, let's say, parameters, be it operational parameters or geometric or material parameters, such that one can confidently say, okay, I can make my device, thin or small or as compact as it needs to be, still fulfill the mission requirements and the performance requirements, while it does not, add up into the complexity and the necessary redundancy of that device. And on a smaller scale, this design margin comes from the neutralizer, which is the smallest plasma system, and the value chain. The neutralizer is implemented into ion thrusters, the most common propulsion systems nowadays. The propulsion systems as well are plasma systems with a lot of uncertainties, so the propulsion developer also adds design margins, uncertainty-driven design margins on his system, and this whole thing is then shipped to the satellite manufacturer, which as well adds uncertainty-driven design margins on top of that, because they don't get the requested data from the EP manufacturers. So this way, design margins propagate from the bottom of the value chain to the top of the value chain and make the final product, the satellite, unnecessarily expensive. So let's talk a little bit about some technical details. This list is incomplete. Just a couple of points here. Especially interested for the audience with technical background. There'll be a runtime adaptivity of the spatial resolution of the plasma flow, which is different towards common nowadays. There'll be enhanced erosion modeling. There'll be thermionic electron emission. We start with noble gas plasma chemistry. Surface charging polarization is available, secondary electron emission, all these features that are very, key features, essential in order to get the physics right. So it'll be magnetic field solver and also an energetic coupling between the plasma, let's say plasma domain, and the solid walls which represent the device. So from a more general perspective, so less technical, the product will be equipped with an easy to learn graphical user interface, including interface specifications which will allow a very easy to set up standard EP configuration for different EP technologies, such that when operating and setting up a test case, it does not require to start from scratch, but you can already solve standard problems in the EP community. So there'll be also drastic minimization of the need to deal with meshing, so mesh generation, mesh optimization. That is, for those of you who deal with simulations, numerical simulation is really a pain in the ass. The whole approach that we implement will allow very easy to perform parametric design studies. And when I say parametric design studies, I don't limit this to let's say parameter material variations or variation of operational conditions. It includes also to some degree variation of geometrical parameters. So there will be an automated support of result interpretation, something that's missing today. This is a big gap, big questions at the end, even if the results look plausible. Still, what does it mean to me? What is the risk in these results? This is absolutely not addressed today. A strong integration of the plasma flow with the EP device, so not just limiting the simulation to the plasma domain, but also going beyond and adding this whole new dimension of let's say spatial scale, which then makes the transition to the whole plasma device. It will be possible to have a full-scale EP simulation on very short time frames. We will ship two things in order to allow for flexibility on the user side. So software that is CPU parallelized and a software that is CPU, GPU parallelized. Massive testing, way beyond what's common practice in the scientific community, and a couple of other points that I skipped here. So to give an example on what is it when you talk about testing? So testing happens on very different scales, from the lowest, bottom one, the so-called static code analysis and unit testing, up to the very end, which is the validation test case. So this is a test simulation, neural test simulation on a solver level, where we use a textbook example in order to see whether the code reproduces not just a textbook example, but also fulfills critical requirements. So-called two-stirm instability, two counterflowing electron beams in front of an ion background start interacting, forming vortices. And if you look at the final result, the real space in X, Y, Z, that you don't really find what you're actually looking for. You have to know where to look at, which is the phase space, where you can really see these vortices that are a consequence of this two-stream instability. So this is, here you see the velocity, and here you see the an X direction, a geometrical direction. So other things that you test are, for example, is the energy conserved, which is a must if you have a closed system, which is the red line here. So this is, those are typical tests performed on a solver level. So we can go even a bit higher on an application level. We see here on the left-hand side, this is a simulation of an electron optics, where an electron beam coming from here, passing through a electrostatic potential configuration, where the electrons get confined, accelerated, and then decelerated. And what you see here is the adaptation of the cross section of these electrons according to the electrostatic potential configuration. With this simulation, I would like to show how we envision to provide information about how erosion evolves over space and time in order to allow a better or an improved design process. Here we have on implication level the simulation of accelerated particles in a novel EP system. Here the low energy, so the low velocity part actually, and here is the exit. To demonstrate where we are at the moment. So this is not really the most up-to-date, let's say status of our work, but it gives a good impression of where we are approximately. So this actually, oh wait a second, this actually brings us to the to our vision. How do we envision plasma simulations in the context of electric propulsion development to be performed in 2022 and the years beyond? Well, mainly by characterized by these 4 points. The first one is, contrarily to the situation today, the users do not need to be or to become experts in applied mathematics and software development, HPC technologies, and with profound experience in knowledge in plasma physics. And the way how we're going to address this issue is that the software that we developed is actually made by electric propulsion engineers, aerospace engineers, mathematicians, plasma physicists, and so on and so on, software developers. You see the team at the bottom, which without it would not be possible to reach this goal. Third point is that simulations done in 2022 and beyond will allow fast coupled plasma device simulation in a predictive manner. So not the plasma system as an isolated problem, but the plasma device as the basis of the problem that's to be addressed and simulated. And the fourth point is that the tool that we are developing will be industry rated and ESA rated tool for the development of those kind of technologies. And one element is that we apply development and quality standards that are common in nowadays software development industry. So we're not doing this alone. We have partners. This is an overview as of today. So we have validation partners here in the first line. This is NeutronStar Systems, which will present right after me. Technical University Dresden and RAS in Stuttgart have confirmed to support us in the validation Ariane group as well. We have beta testers which confirmed already that they will work with early versions in order to tell us what's good and what can be improved. Financial partners here, I would like to mention the Luxembourg Space Agency, which is a very, very strong supporter, not just financial, but also in a non-financial area with their dedication and expertise they put in. We have R&D partners that also contribute to the development of the software and for areas where we for experience and special knowledge that is beyond our capacity. We have, we work with ESA. This is actually an ESA project, and we work also with Francesco Tacogna, which some of you might know him as one of the best and most experienced experts, simulation experts in Europe for such kind of plasma simulation than Hall effect thrusters. So this is an overview. This list is not complete, and we always look for, acquiring additional user requirement. It is very difficult to address everyone in the world who is interested in, how can I say, making the own electric propulsion development more less cost and less time consuming. So if you're would like to interest your user requirements, share them with us, please get in touch with us. We'd also like to develop this product in a way that can integrate without effort and friction into existing and established work procedures. So it would be very supportive if you could share your interface definitions with us. If you would like to support us in the validation, also very welcome. And of course, we would like to have this product deployed earlier, or if you'd like to see features therein which are outside the scope of what we intend to deliver, then get in touch with us. We are open for investments or joint projects on ESA or EU level, whatever brings you and us forward in order to reach that goal. And that actually brings me to the last slide, with which I would like to thank you for giving me this opportunity, and I'm ready to answer your questions.
Okay, thank you, Dejan. If you can share the screen, please.
Yes.
For the attendees, if you have any questions, just write them down on the Q&A. In the meantime, I'll ask you one question, Dejan.
Yes.
Do we need novel plasma simulation technologies for high-power space propulsion systems?
Oh, I would say that's a clear yes. The high-power electric propulsion systems are a very good example how connected these two domains are, which so far have been, treated in a quite separate manner in the development process. If you have a high-power plasma system, there are always losses, and these losses lead to heating up the system, the hardware around the plasma system, and this is something that you have to carefully resolve in order to get your design right. I mean, as in a NeutronStar system case, that's especially important because, as you will learn in the presentation, they have a superconducting technology on board, but also in a how can I say, even without superconducting technology on board, you have much better chances to find configurations of the operational conditions for the plasma and the material and design configurations of the device if you keep these systems and you investigate these systems coupled, because they're strongly coupled. And as we know as engineers, if you transfer larger amounts of heat into a material, the heat starts not just to heat, but it will expand. There will be elastic deformations, potential plastic deformations, changing the properties of this material over time. Erosion comes on top. So these are lots of things that in a high power application become even more critical to be considered as closely connected to, let's say, studies on the plasma systems level.
Okay, thank you. So I have a question here from Dinesh Kumar. Wanted to know how much specific impulse in seconds these plasma propulsions produce.
Well, it depends on the plasma propulsion systems. I think a typical Hall effect thruster, which is the most common technology, I think typical values are, depending again on design and power configurations, I think 2,000, 3,000, 4,000 seconds. I mean, this is hard to answer if it's not more specific. Okay,
I'm gonna move on to NeutronStar systems now. We'll have more questions later after Marcus will give us their presentation. So please stop your video now and we'll get Marcus. Marcus, you there?
Yep, hello.
Perfect. Okay, so the floor is yours. Share the screen. Good luck. Thank you.
All right, so I've just entered the full screen mode. Is this working okay?
Yep, everything is good. I can hear you as well.
All right, so firstly, thanks, Tony, for the opportunity to present. I'm here from NeutronStar Systems. We'll be telling you about Supreme technology, which is our electric propulsion technology for high-power space missions. My name is Collier-Wright. I'm the co-founder and CTO of NeutronStar Systems. I'm here as well with my co-founder, Manuel, who is the CEO. So just to give a brief overview of what I'll be talking about today, I'll give you a quick introduction to the company and introduce the propulsion technology we are working on called Applied Field Magnetoplasmadynamic Thrusters. I'll introduce the combination with high temperature superconductors and how this forms the combination we call Supreme technology before discussing our vision, our business case, and our future plans, as well as the traction that we've achieved in the past months. So NeutronStar Systems is a new space startup. We were founded in December last year, and we're based in Cologne in Germany. Our main focus is providing disruptive electric propulsion systems based on high temperature superconductor technology with a major focus on high power space missions. So we were formed with the support of three main entities. We had IRS, the Institute of Space Systems at Stuttgart, who are experts on electric propulsion with a long heritage of research and development and excellent testing facilities for electric propulsion. Absolute System is a French SME who's a specialist on cryogenics for spacecraft applications with ESA qualified facilities for spacecraft integration and manufacturing. And PI Solutions is Manuel's consulting company, which brings a heritage on business innovation and also a strong expertise on superconductor technology. So a bit more on our background. Our main background lies in two European consortia. The first, called Supreme. This was a consortium of 11 European SMEs and research partners who put together a proposal for EU funding for a superconductor-based electric propulsion system. This was coordinated by PI Solutions in partnership with our two main partners, IRS Stuttgart and Absolute System. Unfortunately, this proposal did not get funded. The second proposal that we applied for last year, called MIST, was also for a superconducting application, this time for spacecraft re-entry shielding. Here we are again supported by IRS Stuttgart and Absolute System, as well as one of our main partners, Teva, who is a superconductor producer from Germany. And here we have in total 10 research institutions from around Europe who are leading in their fields. This consortium is being coordinated by KU Leuven in Belgium. And fortunately, this consortium was funded to 3.4 million euros, with the project is going to be starting in October this year. Just a quick introduction of our team. So you've met Manuel and myself. Among the engineering team, we also have Georg and David. Between us, we have over 8 years of industrial experience and a wide range of different specialities on areas such as superconductors, spacecraft systems engineering, and electric propulsion systems. And Georg has overseen the development and experimental testing of the most advanced prototype of our technology anywhere in Europe, and he's the leading European authority on MPD thrusters. In addition to this, we have a diverse supporting team. They come from many different backgrounds and specialities, and they give us the flexibility and determination that we need to overcome the challenges with which we are faced. So firstly, before I delve into our specific technology, I'll give you a quick comparison of spacecraft propulsion technologies. And this is for in-orbit propulsion. We have chemical systems, which are the classic rockets. You're simply burning fuel and accelerating it to produce thrust. So these are very simple. They let you use a lot of different propellants, and they've been flown for many years. They have a lot of flight heritage. However, they have a low specific impulse, which means they're quite inefficient and they require a lot of fuel. And the control of the propellant is very complicated. Then we have electrostatic systems. This is a type of electric propulsion system. We're using electrical power to ionize a gas and accelerate it to produce thrust through electrostatic means. So these provide a high specific impulse and a high thrust efficiency, and they've been flown already for several years. However, their operation is relatively complicated. They rely on xenon, which is very expensive and rare, and their scalability is poor. They can't be upscaled to higher powers. Finally, you have electromagnetic propulsion. This is similar to electrostatic in that we're using an electric power as the energy source, and this time the acceleration of the plasma takes place electromagnetically. What this means is that we can achieve a high specific impulse, but also a wide range of operation through throttlability and the use of alternative propellants. The problem is that the conventional technologies are currently limiting this technology from flying, and as such, they've had very little flight heritage. So the applied field magnetoplasmadynamic thruster is the technology we are developing. This is a type of electromagnetic thruster. It's a fairly simple device. It's formed of two electrodes, the anode and the cathode. And in between, we have an insulator to prevent the electrical connection between the two. What we do is we feed an electric current between the two electrodes, and this is causing then the establishment of an electric field. We feed then a propellant, which is split between the cathode and the anode, and when it reaches this electric field, it becomes ionized. And now there's current flowing through the plasma, which generates a magnetic field in rings around the central axis. This leads to our first acceleration mechanism of the plasma, called the self-field acceleration. Now, in an applied field thruster, we have an extra coil where we pass the current through, and this generates a further magnetic field, which leads to two more acceleration mechanisms, the Hall acceleration and the swirl acceleration. And in addition to this, we also have a thermal acceleration because the plasma is extremely hot and it gets accelerated through that method as well. So with this technology, there's several different acceleration mechanisms taking place, which makes it very interesting indeed. And this is why it has seen over 60 years of research heritage around the world. This began in the 1960s with the first prototypes built in Stuttgart in Germany. There was also a lot of research done in the United States during the 60s. And then the Japanese started to look at the technology in the late 70s, and they performed actually the first flight mission of the technology in 1980. There was some further research done again by the Americans and by the Russians, with two further flight tests taking place. However, since 1996, there was a little bit of a rundown in the amount of research taking place until 2010, when 3 new prototypes were produced, one in Italy, one in Japan, and one in Stuttgart. And since then, there's been a renaissance in the interest in the technology, with now China also recently producing a leading prototype. Now, I'm going to focus on this one from 2016, which was produced in Stuttgart. This is the operational prototype we have at the University of Stuttgart, our main scientific partner. And here's a picture of it in operation. This is a 100 kilowatt thruster, which is high power, and it has achieved some very excellent results. Steady state operation of several hours, and efficiencies as high as 62%, which is competitive with thrusters on the market today. What I want to show you with this slide is the importance of the magnetic field strength. So I've taken 2 data points here, one at 100 millitesla and one at 400 millitesla. So we're making the magnetic field 4 times bigger. And when we do this, the efficiency is significantly increased. This also means we can operate at a higher voltage and a lower current, which is very beneficial for the thruster lifetime. And in terms of what this means for important operational parameters, we have a higher specific impulse, and we have a higher thrust. So we can get somewhere quicker whilst using less fuel. And this is the importance of increasing the magnetic field. Now, the issue is that this thruster currently uses a copper electromagnet, which is extremely heavy and consumes a lot of power and cannot go higher than 400 milliteslas. So the solution to replacing this component is high temperature superconductors. And here I want to really focus on the importance of high temperature. When people hear superconductors, they think of a traditional superconductor, which is superconducting at extremely low temperatures, and this makes it very hard to be used in space. Whereas in fact now, since the 80s, there's been several new materials discovered which are superconducting at much higher temperatures, and this means that we have much lower requirements for the cooling system, which makes them much more suitable for use in space. So we combine this technology of high temperature superconductors with applied field MPD thrusters to create something we call SUPREME. And SUPREME is formed of 5 main subsystems. We have a propellant and power supply, and this is fed to a discharge unit where the plasma is ionized. We have an applied field module, which contains the electromagnet that produces the external field. And we have a thermal management subsystem, which keeps all of the components at the operational temperatures. So by replacing the copper electromagnet with a superconducting one, we can reduce the mass of the magnet by 4 times. We can reduce its power consumption by a factor of 300, and we can increase the magnetic field strength by a factor of 4, which means we have much higher performances and longer lifetimes. And this is, in the end, technical parameters which we're predicting from this technology. A very wide power range, actually being able to scale down to low powers for small satellite applications, as well as high powers for a combination with Krisol's technology, which they mentioned in the presentation earlier, and also wide ranges of specific impulse and thrusts. So if we compare it to the existing technologies that are on the market, you can take two metrics, specific impulse and thrust. Now, Hall effect thrusters provide a high thrust with a low specific impulse, whilst gridded arm thrusters have a high specific impulse but a lower thrust. What we can do with Supreme technology is offer both high thrust and a high specific impulse, and in fact, we can optimize the operational mode of the thruster to specific applications of the customer. So to summarize the competitive advantages which I've mentioned over the past few minutes, firstly, a very wide propellant flexibility. We can operate on alternative propellants like argon and ammonia, which are 2 orders of magnitude cheaper than xenon. And this also opens new possibilities for hybrid propulsion systems. It's a simple and robust technology and is backed by over 60 years of research heritage in 6 different countries around the world. The technology is highly scalable. We can scale from small satellite applications up to megawatts, and it's a wider range of scalability than any other propulsion technology on the market. And it's highly throttleable, which makes it applicable to several mission scenarios and allows us to optimize thrust maneuvers for individual missions. To put this throttleability into a little bit more context, I have a graph here with a specific impulse against the thrust on the y-axis. What you see there with the blue dots is the grid arm thrusters, and with the red dots you have the Hall effect thrusters. And you notice that both of these technologies are sort of combined to a certain narrow operational range. This shaded blue area is what we can access with Supreme with the use of different propellants. And this allows us to be applicable to several different mission scenarios. And this forms the basis of our vision. So in the near term, we have our market entry scenarios in providing propulsion for small satellites and constellations and geocommunication satellite platforms, followed by satellite servicing vehicles for applications such as debris removal and decommissioning, satellite orbit raising, satellite refueling, and satellite maintenance. If we look towards the midterm, we see applications of the thruster in the lunar gateway logistics, lunar servicing markets, and cargo transfers from the Earth to the Moon. And towards the far term, we have applications near Mars for Mars cargo missions, for crewed Mars missions, and the establishment of a Mars gateway, as well as other applications including asteroid mining and science and exploration missions. So in short, our vision is to enable this next generation of spacecraft missions with Supreme thruster technology. To put this into a little bit of context, we evaluated the opportunity on hand with these missions. We see that these missions can come to the market on regular intervals, driven by the incorporation of our technology, and we're predicting potential annual revenues of over 500 million euros by the year 2039. Just to show that we can actually achieve this, I want to explain to you the business case of our thruster. What we've done is we've taken some reference mission scenarios and we've evaluated the cost savings when we replace status quo technologies with Supreme technology. And this is done in the framework of reduced subsystem masses, higher efficiencies, and reduced propellant costs. So for a geocommunication satellite, we can save up to 10 million euros. For a science mission, such as the DLR Jupiter Moons mission, up to 20 million euros. And for a small satellite constellation, up to 30 million euros. And the savings get even higher for the high power missions. For a moon cargo mission, up to 90 million euros. And for a single Mars cargo transfer, up to 320 million euros, just by using Supreme thruster technology. Our business model is focused on the development of the technology and the securing of this intellectual property rights. And we will combine this with a cyber physical platform, strongly linked with Dejan's activities at SPARC Industries, which will allow rapid development and prototyping of new thruster power classes and new products for our customers. And this will allow us to access our primary revenue stream of selling propulsion systems in 3 main market phases. In the near term, for near-Earth applications, in the midterm, for lunar missions, and in the far term, for Mars and deep space missions. And in addition to this, we also expect secondary revenue streams coming from the application of our superconductor technology to other propulsion subsystems, also to other spacecraft subsystems such as radiation protection and re-entry shielding, and from the licensing of intellectual property rights. So just to give you an overview of where we are going, we're building now on over 60 years of development of NPD technology and high temperature superconductor industrialization. We're at the moment at TRL4, and we plan to get to TRL6 within the next 3 years with the development of an engineering model, followed by an in-orbit demonstration by 2025, after which we'll progress and move forward on the full commercialization in the market scenarios I described earlier. Just to finish off, a quick overview of the traction we've achieved in the past months. So we went to the New Space Business Plan competition in Austin, Texas last November, where we won the Audience Choice Award. We were runner-up at the Satellite 2020 Startup Space Competition in Washington in March. We're top 3 finalists at the OHB Challenge in Inner Space Masters, taking place in October this year. We were named one of ESA's top 50 startups this year, and we're a finalist in the Luxembourg-based accelerator program Fit for Start. And our biggest achievement to date being the capturing of the MISS project for a total of 3.4 million euros in funding. And I'd also like to finish off by just giving you an overview of what the industry thinks about our technology. We've seen there's a big interest in it and a big demand in it. They're very interested to use this technology, and we see that the time is now to develop it in preparation for the upcoming high power market. Not only this, we've recently received some good news. We have been funded to take on an intern for 2 months in the UK by the UK Space Agency. So if anyone is interested to apply and work with us, please feel free to get in touch with us. Or if you'd like to work with us or find out more about what we're doing, please send us an email and we'll be happy to take any of your questions. Thank you very much.
Thank you, Marcus. It's a great presentation. Actually, I think we are dreaming here to have thrusters which are Star Trek like very soon, so we can move into outer space with the plasma sort of means of travel rather than actually fuel. It's great to know actually that this technology is being developed and pushed forward. In fact, I have a question myself. I mean, what is the type of reduction in weight, for example, on a mission? So if you have a similar mission going to Mars or going to the Moon or going to Mars, what kind of reduction in weight would you expect in the actual system rocket in a way? And also reduction in cost as well. I mean, the weight and reduction and cost actually reduce in that effect. Have you made any analysis that actually compares the two technologies? And go ahead.
Yes. So the slide I showed with the value capturing chart was actually the mission cost reductions that we are predicting and that we have analyzed. What is really useful for these types of missions is not only the use of superconductors on the propulsion system itself, but also the combination with Krisol's high power technology, which is an order of magnitude more saving in weight, and also the application of the superconductors for other uses on the spacecraft. For example, you can use it for power transmission lines and control, and you can use it for the shielding of astronauts, for example, when they're in the radiation environment between Earth and Mars. So, of course, it depends on the exact characteristics of the mission, but we did some analyses based on a fully superconducting spacecraft where the mass fraction of the payload, i.e. the amount of space which is payload, can be increased by up to 7% with the use of superconductors. So if you're talking about a 100-ton cargo mission, for example, this is a 7-ton saving, which when you translate that into launch costs alone is huge. Not only this, but the other major saving comes from the fact that we operate on argon instead of xenon. And xenon costs on the order of 2,000 to 3,000 euros per kilogram. And argon costs about 10 euros per kilogram.
Wow.
So for every single kilogram of fuel, you have nearly 1,000 euros of saving, or 2,000 euros of savings. And when you're talking about really large spacecraft where you can have several tons of fuel, then this is another huge contribution to the reduction of the mission cost.
If I may ask, what kind of accelerations? I'm not an expert, of course, in the equations and mathematics of propulsion, but what kind of acceleration, as an engineer or layman in the field, what kind of accelerations and velocities can you reach with your technologies?
Tony, before we go to that question, I just wanted to finalize to comment. You have to consider also that if you go on a system architecture that is going to be considered in ultralight solar power arrays, you will have also substantial, also on top of the savings given by the propellant and also the type of propellant and also the lightweight of the whole total system, you will have also the savings of the mass save with the ultralight solar array. So I think that the overall economic proposition of these technologies is very high, no, and worth to look at. So I'll give you the next question to Marcus.
Yeah, just so the question about the thrust which we can provide. With electric propulsion systems, this is of course the major trade-off to chemical systems, is that they produce generally a lot less thrust. Of course, when you're dealing with large spacecraft, the chemical system becomes impractical because you have to have so much fuel. The only way that you can get both high thrust and a low fuel consumption is with a high power, because the high power allows the electric propulsion system to run at a high enough power that you can generate enough thrust. So we would be looking at sort of similar thrust levels to chemical systems. You're talking about on the order of newtons, so between 1 to 10 newtons, depending on the mission application.
Okay, great. Now let's go to the Q&As from the audience. There are two at the moment. One from Angelo Minotti. Please, can you provide weight and volume for a 100 kilowatt Supreme system? Thank you.
Yes, so the weight of the 100 kilowatt system we're predicting to be 60 kilograms. Just to compare this to the NASA Hall effect thruster, the X3, which they're developing in NASA Glenn Research Center for the same power class, that weighs 240 kilograms. So we have a weight reduction of a factor of 4 there with the use of Supreme technology. In terms of the volume, I'll need to double check and get back to you.
All right, excellent. Adam Baker, let me see. I might ask Adam to speak. I need to find first Adam. Sorry, on the screen. Let's see, Adam.
Yeah, I think he needs to like.
I can see the question here, and I think.
Adam, can you ask a question? So everybody, at least everyone can know will know what the question is, and then you can answer, Marcus. Sorry about that. Adam?
No problem. So thank you, Marcus, for your very professional and clear presentation.
Where are you from and what you do, Adam?
Hey, so it's Adam Baker. I'm the CTO of UK Launch Services and a visiting fellow in space propulsion at Cranfield University in the UK. So electric propulsion is a really exciting area. You guys gave a great presentation. It's a fascinating topic. Well done for your funding win as well. Those EU programs are very hard to win. So my question is regarding MPD efficiency. So typically, MPD thrusters achieve 20 to 30% efficiency at best at those high power levels, the 1 to 10 megawatt range that you aspire to reach. So do you think you can reach the 62% that you've claimed as you go up in power level? Because otherwise you have to increase the input power to give you the high thrust and the high ISP. And kind of the second part of the question, which maybe is a bit unfair, is have you got any life test data to support your promising performance figures so far? Although I guess it's early days, so maybe you haven't done that yet.
So the 62% number has already been achieved with our prototype in the University of Stuttgart, the SX3. This was achieved because there's been some recent progress on MPD technology in terms of reducing the losses through special materials used on the electrodes, in terms of the propellant injection mechanisms, and also all the empirical models and experimental data, of which there is lots due to the large research heritage. There's a very clear trend that the efficiency is always increasing with the strength of the applied magnetic field. So as I mentioned, the 62% number was actually achieved at a magnetic field of only 400 milliteslas, whereas with the superconductors, we are aiming to apply a magnetic field as high as 1.5 Tesla, so nearly 4 times as much. And this is why we're expecting that at least 62% will certainly be achievable, because it's already been done, and we can improve this number even further.
May I ask you something more for Adam? Adam, I noticed that you're taking the data. Just want to make sure MPDs in the order of the 10 megawatts, which have been some of the major multi-megawatt programs conducted at NASA, have been mostly self-fill MPDs, which in the case of applied fill MPDs is a different kind of technology. MPDs are more used for, as you mentioned before, really high powers with supercapacitor banks, etc. I would say that the status quo of this technology is still at a very early stage, mostly due to the problems with the cathode erosion caused by the very large powers used in the discharge. In the case of applied field MPDs, the efficiency values obtained at the University of Stuttgart have been verified by other two entities. One of them is the University of Beijing in Peking, which have also, let's say, a similar prototype to the SX3, and which has verified the already existing result. So the testing and verification work on the technology at that power level of 100 kilowatts has been already conducted. At the low level power, which is up to 3 kilowatts, we have the verification work conducted between the University of Stuttgart and the University of Nagoya with Professor Sasso, which also verify the different acceleration models and scalability models that have been already presented by Hedrich. So the efficiencies you were talking about were placed at the early beginnings, but at experimental prototype level, you have had even AF MPD prototypes providing 50% and 56% running on lithium, or at the University of Princeton, or any others also at the university in Moscow, the Moscow Institute of Aerospace. So the research heritage of the technology, you know, has gone so far that the only trouble to get this technology flying is the exchange of the electromagnet based on conventional copper technology with superconductor copper technology, and that is where we expect and see and believe that we are gonna reach the breakthrough.
Okay, before we bring in the full panel together, one last question from Joanne Wilson. She's asking, in what time frame would you expect electric propulsion systems to be able to achieve orbit raising to the GSO in the same amount of time as it can be achieved with chemical propulsion systems?
With the current power classes, we can't match the time of the chemical systems. Having said that, for a GSO satellite, which you're looking at up to 6 tons, the chemical system will need about 3 tons of fuel, whereas the electric propulsion solution that we provide would need less than 1 ton of fuel. So this is a trade-off for the to be made by the satellite operators. Generally, there's been a very big shift in the recent years to all electric satellites because the savings in terms of launch costs and propellant costs, which are offered by electric propulsion solutions, outweigh the losses due to the delayed introduction of the satellite into service.
You have also to consider the fact that the current platform for geosatellites, geocommunication satellites, they have a maximum of power of 20 kilowatts. And this is coming from the clustering of 4 thruster units mostly. So Supreme offers the possibility to extend the power of these platforms from 35 kilowatts and up. And you can simplify the propulsion architectures by reducing, by having only a main propulsion system for orbit raising based on a 20 kilowatt thruster, and by using a configuration of 3 thrusters for station keeping. So this is the kind of shift where we see the market is going to move once the technology has been validated.
Thank you, Marcus and Manuel. Joanne is from the ITU in Geneva, Deputy Director General of the ITUR. Okay, let's have the full panel on board. Let's get you all together. Just wanted to thank you all for the great presentation and how you work together. Where's Matthias? I don't see Matthias yet. There he is. Okay, excellent. So we
Your micro, Matthias.
bring you all together. So excellent. Hi there. As we let's say wait for more questions from the audience, I have a few questions for yourselves as well, to bring you all together. So let's go. Maybe one question to you all. How has the COVID-19 crisis impacted your plans and activities? Something you can answer all together, one by one, if you like.
Matthias, you go first.
Well, to be very honest, there was not much impact because the main challenge has been the same for more than many years. It's getting access to funding with an international joint venture from the very start. It's so exotic that just nobody believes this is a good idea. I find it hard to believe, but the NASA suppliers had essentially only US partners. And it took me quite a number of years to get them to actually an excitement level to be willing to really openly collaborate with European partners. So this is actually a political friction, which has nothing to do with technology at all. And that hasn't changed through the COVID crisis at all. I think one positive impact is that people are getting used to use teleconferencing. So this is actually an advantage. It's paradox, but it's an advantage. So I cannot even travel to the US, but I still have been able to arrange potential contacts in the US now through video calls or email, and then people are at least getting used to that. So in my view, it's neither a big advantage nor a disadvantage. It's just the same challenge, but the use of video conferencing has been normal now, which in my view is actually rather an advantage. So it's still slow, but I don't see a dramatic. There's no short-term problem. I think what we present here is really long-term visionary, and it's totally disruptive. And if you want to go to Mars, and this is my conclusion, if you really want to go to Mars and you don't choose this technology, you should better stop talking about this, because it's just a waste of time and money to use old technology to go to Mars. That's my conclusion. Is that enough for you?
Dejan.
I'd like to, without repeating the last words, so I would like to confirm these last words. That was very, very wise. Perfect match. But regarding the original question, luckily, if you develop software, you do not really depend on complex supply chains. So the issues that we faced so far directly are actually quite limited. So that's, sort of okay, acceptable. We would, however, expect some impact, which depends on how the COVID-19 situation, let's say, affects other players in the domain, other players in the community. Less startups, but more, medium and large-size companies. This is something that we observe, because we expect quite some impact on how we will access the market, and how we, how can I say, structure or modify, if necessary, our strategy.
What about you,
so not in a negative sense. Sorry for in case that was unclear. So we actually expect, just in from a pure, let's say, competitivity perspective, potentially positive impulses. It sounds weird, and it's just a pure, economic perspective, not more.
Okay. Well, I mean, we were in the middle of fundraising activities when COVID came. So for us, this was quite disappointing, because we were running for different programs at Luxembourg, for example, for Fit for Start, which we were supposed to present in March, Space Up in Rome, and Hello Tomorrow. So this, of course, brought a tremendous delay on our in fundraising activities and our investor money searching. However, in the process of getting these fundraising activities, I mean, we identified different shortcomings in our overall presentation and overall offering to the market, and that's what we're going to do. What we're doing now, no? So we're working on different ESA tender projects. Working on some preparations for the EU project, doing other consortia activities with companies like SPARC, and also with our partners from Krisol. So all in all, we are now prepared for what is to come now, and we're going to be focused on securing the IP mostly, and taking this time to prepare for the next fundraising that we just hopefully to start in some months.
Thank you for that. Pierpaolo Gigino, I think you have something to say or to ask. Pierpaolo, go ahead.
Yeah, well, first of all, congratulations. I think what you're doing is quite brilliant. It's logical, at the same time, it's very brilliant. I have a question, which is, I'm no expert on plasma generation control, but I have a question on what do you feel is going to be the plasma temperature, the peak plasma temperature in your system, and when you are going for the very, very high magnetic field control. And do you expect, and the question is both to Marcus and Dejan, do you expect any effect in modeling and control due to highly nonlinear effects?
I'll answer the first part of your question. Plasma temperature, we have to be a little bit careful what we're referring to. There's a lot of different definitions. In terms of for me as a system engineer and a propulsion engineer, the main impact of the plasma temperature is on our thermal management system, which is a major challenge and one which we are working on a lot, and we're devoting a significant focus to. So for this, we are expecting that the plume may have a thermal load of up to about 2000 Kelvin. So we're looking at some very special high refractory materials and some multi-layer architectures for the production of the thermal insulation. As opposed to your next part of your question on the plasma modeling,
I think it's still too cold to actually have an issue, but I think that the question is, when you control it, do you have foreseeing the effect of highly nonlinear effects, which actually happen in plasma, not for various interactions? And are you actually foreseeing any? They can be positive or negative, of course, when you have these things, but they're difficult to judge, to model. So are you actually foreseeing some effects in that space? Although I have to say, it's still relatively cold to actually have a nonlinear effect. But, you know, the question is very much to you.
I can just help a little bit of regarding the plasmas. I mean, if you're talking about fusion plasmas, etc., probably you're going to be talking about the kind of high energy plasmas that shows this kind of physics phenomena.
Absolutely, you're correct. That would be much hotter.
Okay, this is a low energy plasma regimes, and I think that Dejan can give you a little bit more of insight on how do you control that, and if you see these anomalies at all.
Not anomalies, some nonlinear effects that actually have to be included in your modeling. Usually are a bit of a pain.
Dejan,
because they're difficult to model. Their own set is you know, occurs suddenly, and then it starts to dominate things. I must admit at that temperature you probably don't, but you know.
So what has been done in the past in order to simulate MPD thrusters is to apply so-called continuum codes, plasma codes, which was okay and working for the, let's say, self-feed MPD systems. Here in the NeutronStar systems design, it's essentially an applied field magnetoplasmadynamic system, which operates at significantly lower mass flow rates. The continuum codes applied in the past failed. They failed. It could not be clarified why they actually failed. There are potentially different reasons why they failed. There's one explanation that there have been significantly non-continuum regimes that could not be properly addressed with a continuum approach that was implemented, leading to a failure in the convergence. And another possible cause is that the anomalous diffusion of the electrons that has to be considered if you have magnetic fields, and here even more because we have very strong magnetic fields, is not something that you can, provide easily as an input parameter. So this happens, and you have to provide this number if you have actually two standard modeling approaches. The one is if you go fluidic, then you need to provide this parameter, and this parameter is extremely crucial. Yeah. There's not one theoretical approach that can be applied without doubt to the whole simulation. It's extremely difficult to measure something from an experiment, and even if you would do that, it would be more like matching simulation data to the experiment, which you don't want to do. And the second way to approach this problem is if you go fully kinetic, and ideally you go 3D, because if you just go 2D, then you still have to define an approach an approximation of that value because you ignore the third dimension. So the only approach, the only reasonable approach that I see here is indeed to be 3D, fully kinetic, in order to address nonlinearities that actually has their origin on a microscopic level and are very hard to be described on a macroscopic level. Turbulences is one of these examples. Turbulence models have been worked on since decades, but their origin is on the microscopic level. So that's the approach that I would recommend. And I'm definitely not saying that's easy, especially in a high power system where you have, due to higher let's say the higher power levels that you put in, you have significant, let's say, complications in a chemistry. You might have radiation effects that you need to consider. You have to be aware that surface properties might change over time. I'm not talking about erosion here. The best, how can I say, if we talk about predictivity, you have to make the model as independent as possible from of experimental data that you need to put in order to make it work.
Okay, I don't
know whether it answers the question, but hopefully it does.
Thank you very much. Yes, I think it did. I agree actually with your approach as well.
All right, I'm going to move on to maybe a question to Matthias, and then maybe we need to wrap up. Matthias, how sensitive is the power generation for long missions, especially those missions when flying to Mars, due to the reduced solar radiation intensity as you get closer and closer, away from the sun, in a way?
Okay, do I understand correctly? That mean, is the question how much is it reduced due to the greater distance from the sun? Okay. Yeah, this is actually quite a simple calculation. You can just look up the table from AM0, or solar power with respect to distance. It is, of course, you're correct, the power will decrease. So the specified, for example, 50 kilowatts for this 400 square meter is at AM0 in geo orbit. And if you go to Mars, this is reduced. I can give you the exact figure later, but you can just check the table, how much is it reduced. It's not an order of magnitude, but it's significant. So it's like 20 or 30% at least. But you can look up in the table. I don't know that figure by heart. I can tell you by email.
What about the biggest advantage of ultra-low specific weight PV arrays for space applications? What's the sort of biggest advantage of these?
Well, I said the only disadvantage is the higher area. That is clearly a disadvantage. That is absolutely agreed. But when you see that the solar cells are actually flying successfully, that means it has been proven that this deployment structure is actually working. And the biggest advantage I see in the ease of the stowing. When you look at, for example, ESA is producing a call for just giving a budget to provide several different designs on how you deploy a large power area, just because they think deployment of a solar cell is the biggest issue. If you start working with a foil, the deployment is already solved. So this issue is simply gone. You don't have it anymore. So if you go in a different direction using different technology combinations, It's a bit like Bruce Willis in Fifth Element. You just start at the higher level. You're in a different level. You forget about everything. So I would say the biggest advantage is the ease of stowing, high stowing density. And of course, the reduction in weight, which is absolutely dramatic. The bigger you are, it's almost proportional to the power. So the bigger you are, the better. It's a bit paradox, so you cannot really use it at a CubeSat. I would honestly say that working with a CubeSat and this technology doesn't really make a lot of sense. But if you are big, then it's huge. The advantage is really huge.
All right, excellent. So maybe one last question as we close, just reminding the attendees there's a poll in progress if you want to answer the poll. Generic questions to everyone in the panel. How does SPARC's expertise on plasma physics and simulation tie in with the efforts of NSS?
Well, okay.
Who wants to answer that?
Yeah, I mean, it's pretty simple. SPARC industry is going to help us to save a lot of money by reducing the amount of thruster design, building, and testing cycle. SPARC Industries coach technology will give us the chance to maximize the design phase of our thruster, and will give us also the chance to verify numerically and experimentally our scalability laws. So the one cannot go without the other, if you want to see it like that, because you also need to understand what's going to be the not only the interactions between the plasma plume and the thruster itself, but you need to also understand the spacecraft interactions. And here is where his tool is going to give us a lot of insights, especially in terms of how do we operate the thruster? What is the best mode of operation of the thruster? You know, and what operational envelope is going to be the best to assure spacecraft integrability, integrity, and also mission cost efficiency. So we go together by the hand, so to speak. Thank you.
How the hell I'm supposed to top that?
You don't have to. You're basically helping their company to actually save money and actually be more, let's say, prompt to build new engines, basically. So
that's exactly the mission. If we talk about added value, it differs whether you talk about added value from a scientific perspective or talk about added value from an industrial perspective, and that's the latter part is the one that we focus on, and it just needs a tremendous change of perspective in order to get things right and set the right priorities, and having partners, one partner, multiple partners, which support this activity and support demonstrating the economic added value is absolutely crucial. So we are very happy about this, the collaboration and the opportunity to demonstrate what we can actually do for others in order to make development less risky, faster, and less expensive. It's as simple as that.
It seems that you have a great tool actually, and but likely will require an evolution for improvements into the technology likely. So it's not an easy tool to create, especially with the mathematics behind it and the physics behind it as well, which often you try to linearize, like Pierre Paolo was saying before. There's a lot of non-linear effects, but which you need to linearize when you integrate. Anyway, Matthias, go ahead and answer the question from Lorenzo Ricciardi. Can you ask? Can you read the question?
I repeat the text. With very light and large structures, are there going to be any problems for attitude control? To be honest, I cannot answer it myself. I just give you a very plausibility answer. I mean, the fact that these sails at 400 square meters are successfully flying currently in missions with NASA means that they somehow have this under control. In principle, it's correct. This risk increases with the size. But I guess the biggest risk is when you go lower to the atmosphere. So if you, for example, work with satellites in lower Earth orbit, when you have a little bit of remaining friction from the atmosphere there, it's possible that there is some risk which is a bit more challenging than without atmosphere. But the main application is, I guess, between outer atmosphere and Mars, where you have absolutely no friction. So I think it's not a dramatic issue, and the fact that it's been flying in space successfully seems to show that this seems to be no issue. I cannot answer you from my own track record. If you want, I can check with my partner Nexolf and tell you what it means. If it's more challenging, I think it's under control, but I'd have to double check, to be honest.
All right, excellent. So we're now going to close the panel. Any last words from Manuel, Marcus, and Matthias and Dejan before we close? Anything else to be said by yourself? Thank you so much. I'll just say thank you so much for your presentations.
Well, Tony, I mean, 150 participant registers, great technique, great moderation. Thank you a lot for having us here and giving us the chance, and for putting us in your network and giving us, this opportunity to increase our visibility and what we're doing. So from our side, many, many thanks.
Yes, indeed. Also from our side, that was very helpful. To present and to reach out with a topic that is really very technical and hard to digest and also hard to explain, especially if the audience is heterogeneously composed. So that was a very, very fine webinar. Thanks again. And yeah, hope to stay in touch in the future. And, maybe we have the chance to present after, I don't know, a couple of months. Deliver an update where we are then.
Absolutely.
Matthias?
Yeah, maybe one last word. I was already born when John F. Kennedy actually announced the Apollo 11 mission. And if you think back about the ambitions they have with primitive technology, this is still, in my view, absolutely amazing. I think we need leaders today who just stand there and say, in 10 years, we will be on the Mars. We don't know how to do it, but we will get there. Something like that. And that's about, I think, the challenge we have today. So there's enormous pressure to guarantee technical performance before you even finish your PowerPoint presentation. That is a bit frightening, because what we discuss here is really one higher level of innovation, which is just so much better than anything you know. There's a certain risk, absolutely, but I think it's worth it. And the maturity is surprisingly high, and the remaining risks, in my view, can be controlled. They are hard work. We have to invest, yes. But if we want to go, then this is my conclusion. If you really are serious about going to long-range missions, for example, with humans, then you need so much more payload to do something useful. You should stop thinking about using old technology altogether. Just totally. Either you do it professionally, or you forget about it. That's my summary.
Well, thank you, Matthias. I hope that we don't get a SpaceX, after us.
Yes.
Well,
one day take it to the Mars.
Thank you for this one, Tony. Really great webinar. Thank you a lot.
Thank you. The only thing I would say is that we need this new technology to take us from the ground on the Earth into space, and that's we're not there yet, I suppose. So one last request: just smile on the screen. I'll take a screenshot of a nice photo of this webinar now. Perfect. And I wish you well, and thank you so much for joining us, and I'll see you next week again. All the best.
Thank you, Tony.
Thanks again. Thank you. Bye-bye.
Bye.
Thank you.